Hello everyone. In the last lecture we looked at power handling devices or components in photonic integrated circuit. So, now let us look at how one can manipulate and handle polarization in a photonic integrated circuit. Let us look at those devices. So, light polarization is an interesting property that we have in a photonic in photonics, right. So, you have electric and magnetic field that are orthogonal to each other. So, you could have this configuration or the other configuration where you have electric and magnetic field. So, you can have one of these configurations. So, when you have these configurations, right. So, whether light is going into the slide here or coming out. Okay. So, the electric field can take transverse, right, or the magnetic field can have transverse component. So, these are all two different solutions on its own. So, they are orthogonal solutions and they do not talk to each other, right, because they are isolated solutions, they are eigen solutions in the system. But then more often you want to manipulate or you want to filter out these polarization, right. Sometimes you could have unpolarized light, but you want only TE polarized light or only TM polarized light in the circuit. This is all for having a clean circuit. So, you want a single polarization to handle all the circuit functionalities, let us say. So, if that is the case, we should be able to filter out polarization, and that is what we call polarizers. So, we use polarizers to filter out only one kind of polarization out of randomly polarized or unpolarized light, let us say, right. If that is the case, then if the input is TE or TM, right, both are combined, right, then you want to only take out TE, right. What kind of functionality can I do, right. So, one easy way to do that is by using a very simple metal on top of the waveguide, right. So, this is transverse electric and transverse magnetic, right. So, the magnetic in TM waveguide, right. So, in TM configuration the electric field is vertical, right. I only want TE, right. I do not want TM passing through my waveguide. So, one way to handle this is by creating a high loss for this TM waveguide. Okay. So, just to conceptually look at this, let us take this is TM configuration and let us say this is TE configuration, all right. So, when the light is propagating through a waveguide, so this is a very simple waveguide, let us say, right. You could have electric field this way or you could have electric field this way, right. This is TM and this is TE. So, they are propagating through this waveguide, right. So, you have TE and you have TM going through, but there will be an associated loss when it propagates through this system, right. So, let us say you have alpha times TE is what you get at the output, right, and then you have alpha times TM is what you get at the TM. If the loss that you have, right, so alpha is loss, let us say, right, that is mode loss for this. So, if you make this loss specific to the polarization, so this is alpha for TE and alpha for TM. So, if alpha for TE equals to alpha for TM, then you will get both the polarization out, right. So, in case of alpha TE equals to alpha TM, input is TE TM and the output is TE and TM, right. So, this is what you would get. But then if I take a scenario where alpha of Tm is much greater than alpha for Te, then my input is Te and Tm, but only Te would survive, right. So, Tm would be lost inside, right. So, this is what polarization or polarizers do. So, they just kill one of the polarization by creating a higher loss for one of the polarization. And how do we achieve this? So, this is the concept, right. So, you increase the loss for one of the polarization. So, how do we achieve this? So, we need to have high loss for this Te mode, right. So, Tm mode here. So, this electric field should be absorbed. So, we know from the basics, right. So, if I put a metal has very high refractive index and your E field should interact with this metal. So, when it interacts with this metal, it can create surface plasmons here. So, there is a plasmon mode that can be created here. So, because of interaction with this metal and creating a plasmon mode, you will actually generate a propagating mode inside the metal, and basically the light from this would leak into the metal for the electric field that is pointing vertical. But for light polarization where the electric field is horizontal, that is the Te polarization light, it will not interact with this metal. When it does not interact with this metal, it will just propagate through the medium without any loss. But then for the light that is having interaction with, right, so with the metal, this light will be lost into the metal to create solution into the metal, and then they will leak or absorbed in the metal. Okay. So, this is how you create a preferential loss between the two polarization. So, using a metal is one example, right. So, metal acts as an absorber for Tm polarized light. So, because the Tm polarized light, the electric field is vertical, and for Te polarized light it is horizontal. So, because it is vertical, when you put a metal on top, it is going to absorb this vertical field. So, there is a phase matching condition. So, those are all details that I am just leaving conceptually to understand this. So, the vertical E field will absorbed by this vertical metal on top. But then for the horizontal E field, it will not interact with the metal, because the metal is too far for the field to interact. So, this is how you can design your structure to create preferential loss for one of the polarization. For example, if I want to absorb light that is with Te polarized, right, I can put absorbers on the side. Okay. So, the light is sitting here, and then I can put a metal the side. So, then there will be an interaction of the field and it can couple out to the metal. Similarly, what happens for the top metal, all right. So, you can create preferential loss for Te and Tm that would result in polarizers. So, that is the first kind of polarization, right. So, you are killing one of the polarization. So, you do not want one. Okay. And the next kind of device is how do we split the polarization, because when we say we are going to kill one of the polarization, that means that the whatever energy that is present there is lost. We are not making use of that. Okay. When you have information both in Te and Tm polarized light, you want to capture both this polarization in order to understand all the information that we have there, right. But then by removing one of the polarization, right, you only get half of the information, right, provided that the both Te and Tm carry 50% of the information, let us say. So, you are losing that 50% of intensity that we had. right. But the information that you get from TE is the same information that is present in TM as well, but then the power that was carried by TM waves are lost, right. That is not very efficient way of doing it. So, in order to capture both the light sources, we can have polarization splitting and then you can capture it, right. So, that is what polarization beam splitters do, right. This is the functionality that exists in the bulk optics as well. So, when you have two polarizations here, the device or the component would split the polarization. So, TE in one and TM in the other. So, this can be easily understood from our anisotropic material concepts, right, because you have the fast axis, slow axis, and one polarization is sees a different refraction compared to the other. So, that you can split these two polarization in space and then you can collect them. In guided wave optics as well, you could use a directional coupler based approach by using an anisotropic substrate, right, or some sophisticated directional couplers, right, which we will see later on how one can split the polarization between two different sources. So, this is also something that we can do, all right. So, now we can completely take out one polarization and we can actually take information from both the polarization by splitting them. Okay. So, there is no mixture here. So, you are splitting them, and the next concept is to convert the polarization. Can I convert a light that is TE polarized to a TM polarized, or TM polarized light to TE polarized? So, all you are trying to do, whether I can rotate these polarization the way that we want, right, in order to achieve a different orientation of electric field. It is indeed doable. The way that we do is by using polarization rotators in a passive form, or you can also use electro-optic converters. So, you can use electro-optic material, something like lithium niobate, in order to convert this polarization by using periodic arrangement of these electrodes that will allow rotation of this field or creating alternate refractive indices that will allow this phase matching between TE and TM. So, that is another way of handling polarization conversion. You can also do it through passive means similar to what we saw here. So, you could have TE come in and then you can rotate the polarization, but not in a single waveguide. Perhaps you can have some structuring along this that will rotate this polarization, okay, which is something doable, or you can do directional couplers as well. So, you can take in a directional coupler configuration where you put TE light here and then you get TM light in this case. So, when it is transitioning from the bottom waveguide to the top waveguide, you see it is becoming TM, and while the through port will have TE polarized light. So, this is another way of realizing polarization conversion in a pure passive nature. Okay. So, this is all about phase matching your TE with TM, and these concepts we will see later once we go into the details of this device. And finally, let us look at waveguide components that interact with other form of energies, right. So, electric field and acoustic fields. Okay. So, what can we do by using this? So, a primary thing that we use for many application is phase manipulation. So, when you have a light wave of a certain phase come into this device, you want to change the phase of it. Okay. So, you want to have a slight phase difference that you add to this device. Okay. So, add to this wave that is propagating through this device. So, how can we do this? It is basically changing the material property. So, I take a bulk of a material, and if I transmit a wave through it, right, because of the refractive index change, right, if this is n equals to 1 and let us say n equals to 2. Okay. So, when it is passing through this medium, right, it is slowed down, right. So, that means it will accumulate a certain phase, and when it is going through just n equal to 1, let us say free space, there is no phase difference from point A to point B, right. And when you have a medium in between, it changes. But now the question is, can I dynamically change this phase difference? Right, now it is static. It is indeed possible to do it by using electro-optic effect. So, the refractive index that we see here, right, is a function of electric permittivity, right. So, we all know permittivity is a function of electric field for isotropic anisotropic materials or electro-optic material, right. So, when you apply a certain electric field, the refractive index would change. When the refractive index changes, the phase would change, right. So, this is how you can make a phase change to a light that is propagating through this device, which is called a phase modulator. So, you can change, you can apply a DC or you can apply an alternating current. So, by applying an alternating field, you can change the phase, oscillate between 2 delta phis, right. So, if you want a constant change, you can apply a DC, right. So, when you apply a DC, you should be able to change this phase only in one direction, all right. So, what are all the other things that we can do by using this electro-optic or phase change? So, by just taking the same configuration, right, I can take this and combine these two. Okay. So, by doing this, you can create an interferometer, right, and now this interferometer again is static, right. So, but when I apply an electric field here, my phase is also changing dynamically. So, because of this dynamic change in the phase, I can change my intensity here as well, okay, as a function of time. When my electric field is changing as a function of time, I can change my optical intensity change as a function of time, because you are changing your phase, right, as a function of time. So, that is what we do in order to realize a intensity modulator, right. So, you want to change the intensity of light passing through this device by an external stimuli, right. So, the external stimulus here is an electric field. So, by applying an electric field in this interferometer, it is called a Mach-Zehnder interferometer, you can change the light intensity that is coming out. And finally, you can also use Acousto-optic interaction, which is used to create frequency shifts, right. So, you can take a certain frequency coming from an acoustic transducer, right, some piezoelectric material, let us say, and you create this field, and this field is going to interact with an incoming frequency, right. A modulated light or an unmodulated light, you are going to interact with this, right. So, with the frequency coming from the surface acoustic wave here, right. The surface acoustic waves are going to interact with the incoming optical waves, and they will mix, right, and this is basically frequency mixing, and this will generate frequency side bands, right, that are placed delta f apart, right. So, this is f naught and this is f naught plus f saw and f naught minus f saw. So, these are all the side bands one can generate from this Acousto-optic modulators. You can create new frequencies coming out of this, right. So, you can have an unmodulated one, or this whole input signal could also be already a modulated signal, right. So, there are interesting optical or RF signal processing that you can do by exploiting the optical on chip optical signal processing here. Okay. So, with this device there are a lot of material aspect involved here as well, but there are interesting signal processing strategies one can do at very high frequencies that sometimes are impossible to do it with traditional microelectronics based circuits. Okay. So, with that we have come to a summary of end of the summary of this components, right. So, integrated photonic components that we can use for realizing various functionalities. So, this is not a comprehensive list. Okay. So, what I given you is some of the important concept devices. So, you can build on top of these devices. For example, we have not discussed cavities. So, you can create optical cavities by using a waveguide. So, that is again a very important component, but then that component could be realized by putting some of these components together. For example, a simple cavity could be realized by the grating reflector. So, we talked about reflectors in the last class, right. So, you can put two reflectors and give a gap between this, right, a cavity between the two mirrors, that will give you a very nice cavity that you can use it for realizing a laser, for example. We can also use this for polarization manipulation, right. So, you want to capture all the light that is coming to you. So, how do we do that? By using this cavity, by using this polarization splitters, right, and you can use power combiners later on in order to capture this. So, combining these fundamental blocks, you can create more complex functionalities, and this is not a comprehensive list. There are much more discrete functionalities people are coming up with by combining material aspects with light matter interaction as well. Okay. So, with that we have a comprehensive understanding now with different type of device or components that we have seen so far. We had power handling, we had polarization handling, and we had some active interaction with electric field, acoustic fields, right, by combining material aspect as well to realize a certain functionality. Going forward, we will look at each and every component that we just discussed into their physics and how it actually works. Thank you very much.